Look around you. The fan spinning above your head, the lights in the room, the screen you're watching right now, they all run on electricity. We rely on this energy every day, yet we rarely pause to consider what is physically flowing out of the wall socket. To understand this flow, we examine the building blocks of matter. At the atomic level, a substance consists of a static nucleus surrounded by negatively charged electrons. In conductive materials like copper, loosely held outer electrons detach from their orbits and drift freely between atoms. A single wandering electron has a negligible effect, but electricity occurs when billions of these particles are forced into a coordinated, directional flow. We define that flow as electric current. Measured in amperes, current represents the rate at which these electric charges pass a specific point in a conductor. Naturally, electrons move in random, chaotic directions. They will not organize into a unified stream without an external force acting on them. That force is voltage, also known as potential difference. Think of voltage as the electrical pressure required to move electrons through a wire. In a water system, an elevated tank creates pressure that forces fluid through a pipe. In a circuit, a battery provides that same pressure, pushing electrons through the conductor. Repelled by the negative terminal, these negatively charged electrons are pulled toward the positive one. Historically, scientists originally assumed current flowed from positive to negative. We still use that convention on paper today, even though the physical particles are moving the other way. Voltage and current are codependent. Without the pressure provided by voltage, the movement of the electron stops immediately. For voltage to maintain its push, the current needs a continuous, unbroken path to travel through. This is what we call a closed circuit. That path is not a vacuum. As billions of electrons surge forward, they constantly collide with the stationary atoms of the wire. This physical opposition to the flow of electrons is called resistance, and we measure it in ohms. George Ohm discovered that these variables are locked in a mathematical balance called Ohm's law. If you increase the voltage, the current increases with it. But if you increase the resistance, the current is forced to slow down. We use this relationship to manipulate electricity, adjusting the pressure and the obstacles to control exactly how fast those electrons move. While resistance opposes the flow of current, those constant atomic collisions produce a specific byproduct: intense friction and heat. Engineers use high-resistance materials to capture this effect. These concentric coils are designed to maximize collisions, converting electrical flow directly into thermal energy. This engineered friction is what allows an electric iron, a toaster, or a space heater to function. We measure the rate at which this system converts electrical energy into real-world work in watts, or electric power. Appliances function as calculated friction zones, engineered to harvest the energy shed by those moving electrons. Heat can also be a danger. If too much current is pushed through a wire that isn't designed for it, the resulting heat can melt insulation and cause fires. To prevent this, we use fuses. A fuse contains a thin metal filament, a deliberate weak point designed to melt and break the circuit before the rest of the system can overheat. We also use earthing, which provides a low-resistance safety path into the ground for any leaking or excess current. Every time you use an appliance, you are engaging a system that spans from the microscopic detachment of an electron to a massive, regulated power grid. Flipping a switch completes this circuit, directing the flow of billions of invisible particles to safely perform work on your behalf.